Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Comparators. Comparators are another one of our common functions of combinational logic, and in its most basic form, all a comparator does is determine if two numbers are equal to each other. They are not equal to each other. They are obviously unequal to each other. We can extend that inequality to something being greater than or something being less than. But again, in its most basic form, it's testing if two numbers are equal. And if we go back to some of our more basic logic gates, think of the description of equality. If it's the same or if it's different. Think about those logic gates. Which logic gates test if something's same or different? And those two gates are the exclusive OR and the exclusive NOR. And there's our description of the exclusive OR. High output if inputs are different, exclusive NOR, high output if inputs are the same. Okay, so it depends whether you want a sourcing or a sinking output, either an active low or an active high output. So for the example of an exclusive NOR, what I'm going to do is put number A on there and number B on there. When they're equal, they're the same. So it will output a high if A and B are the same. Now, we can't necessarily just limit ourselves to 1-bit numbers. I want to test for equality on a 2-bit number, a 3-bit number, 4-bit number, so on and so forth. Think about equality if everything's the same. So what you're going to do is you're going to test every single bit position from the LSB all the way to the MSB. And if all of them are the same, the whole numbers are equal. So let's say A is now a 4-bit number going from A3 to A0, and B is a 4-bit number, B3 to B0, MSB to LSB. What I'm going to do is going to test every single bit position. And if all of them are equal, I should output a high if they're all the same. So how would you think you would do that? So using some of our basic gates. Well, obviously you're going to use an exclusive NOR. Okay, because we want an active high output for this case. How do I synthesize all these? Well, they all have to be the same. Think about an AND gate. Okay, so the function would look something like this. Okay, so what it has here is our A inputs, MSB to LSB, and then our B inputs, MSB to LSB. And what's happening here is the MSB is compared, the next one down is compared, the next one down is compared, the LSB is compared. And what's going to happen if every single one of those bit positions are in fact equal, they're sending a 1 to that individual AND gate, and it's saying a 1 there. So let's just compare the number 1010 with 1010, that being A3 to A0, B3 to B0. Obviously, you're going to place 10, 1 0, 1 0, 1 0, 1 0. Take the MSB, they're the same, it's a 1. 0 0, they're the same, it's a 1. 1 1, they're the same, 1 0 0, they're the same, 1. And we get those all ones routed to that single AND gate at the end, and obviously they're equal. Now, go ahead and change that bit position right there in the A, the LSB. What happens here is all the other AND gates, all the other exclusive NOR gates remain the same, those outputs with the exception of this one. It is now supplying a 0 because it is not equal. The LSB is not equal. So it's sending a 0, and that AND gate is receiving 1110. The output of an AND gate is high when all inputs are high, all inputs are not high. A does not equal B. It's telling you that there is inequality in there. Now, the point comes in, which way is it? Is it higher or less than? Okay, is it greater than or less than? So the inequality can take two forms. Number A can be larger than number B, or number A can be smaller than B. So it sounds like we have 3 outputs. We've got 2 inputs, and when I say 2, I'm putting a quotation mark about that because A can take the form of a multi-bit number, so can B. So I've got A inputs and B inputs to a comparator, and it's obviously producing an A equals B out. If they're equal, it's going to go ahead and signify that as a high. But there are 2 other possible occurrences. A could be greater than B, A could be less than B. And my question to you before we even go into the next step here, these outputs here, the 3 outputs, can there ever exist a time when 2 or more of those are true? And the answer is no, never, you're wrong. Because A cannot equal B and simultaneously be greater than B. Does that make sense? Okay, 5 can equal 5, but 5 can never be greater than 5, or 5 can never be less than 5. Example, 6 can always be greater than 3, but 6 can't equal 3 and 6 can't be less than 3. What I'm saying is these 3 outputs, only one can be true at a time. 3 outputs, only one of which can be true at any time. And I'm saying 2 quotation mark inputs because A and B can take a multi-bit form. It can be a 1-bit comparator. It could be a 2-bit comparator, 4-bit comparator, 8-bit comparator. And I'm going to put a plus behind that, 2 plus inputs, because we'll see when we go into cascading these things, i.e. taking a large bit stream and comparing them, I can potentially pass information from a lower order to a higher order, very similar to what we've done in our adder discussions. Basically a structural approach, letting ourselves to a structural approach. And cascading, I mean, think about like a waterfall, a cascade. It's going from one level to the next level to the next level. In this particular case, what we're going to do is we're going to compare bit positions from, just think about how numbers are organized, the MSB. If A3, let's use this as an example, A3, A2, A1, A0, and its number B3. It's being compared with B2, B1, B0. Regardless of the value of these lower orders, what if A had a 1, A3 had a 1, and B3 had a 0? Regardless of what those numbers are, I'm talking about these numbers here. Which is bigger? Okay, it's pretty obvious. A is a bigger number because that is the MSB. So there's a relation between those higher order and those lower orders. But now let's say, for example, if our MSBs are equal, we'll go on to the next one. So what we're doing successive comparison. If we've not determined if one is greater or less than using the MSB, step down to the next one. And let's say that those are both equal. We've got an equality. Let's go down to the next one. For an inequality, which one is greater now, regardless of the value of A0? It's pretty obvious. B is greater. So it sounds like there's going to be a relationship that's forming. Brief divergence, though. We did, in a previous take-home assignment, develop the K-map expression for a 2-bit comparator. And what we had is number A1, A0 being fed into a comparator. And we developed the expressions for A equals B, A is greater than B, A is less than B. And I'm not going to give you the answer because, again, it's a take-home assignment. I know some of you guys are probably advanced in the lecture to go ahead and see what's going on, but it's super easy to set up. I'm just going to show you the setup for this. A1, A0, B1, B0. Those are my inputs. Exhaust all possible combinations of inputs. What are my outputs? A is greater than B. A is equal to B. A is less than B. When A is greater than B, put a 1 there. All the other ones are obviously 0 because A can only be greater than B in that particular circumstance. If A is in fact equal to B, put a 1 there. If A is less than B, obviously put a 1 there. Just basically, it's just exhaust all possible combinations of input. Think about it for this one. Think about it for that one. Think about it for this one. Determine the appropriate outputs. What do you do with those things once you've developed the truth table? Take the truth table, put it in a K-map, a 4-variable K-map for A is greater than B. Entirely separate. Take that truth table for this column. Put it in a K-map for A equals B. Come up with a minimum logic expression. Finally, you guessed it, move on to that next column for A is less than B. Put it in a K-map and come up with the expression for A is less than B. I'm not going to give you the answer for this. We have already gone over it in lab. This, again, was a take-home exercise, but you should be able to do this. And hopefully you're going to come up with the same answer that we came up with in lab there for the review. The point being is that there are 3 separate outputs based off these 4 input combinations. That is a way to do a comparator. It's a way to do a 2-bit comparator. What we kind of run up against the wall here is this, the ability to do this in a K-map. I want to do a 3-bit comparison. And that's a 6-variable K-map. Things are going to get a little bit more complicated, okay? I might be able to come up with a structural approach that might be able to help me out where a single bit comparator is being used to pass information back and forth. Before we go into that, I do want to do this concept of cascading. Like I said previously, there are 2 quotation mark plus inputs. Okay, and this concept of cascading is I can have lower order comparators passing information up to the next higher order comparator. The higher order comparator takes precedence. But if there's an equality shown in that higher order comparator, it's got to take information from the lower. Okay, so what I'm going to do is just draw a simple diagram on what I'm talking about here. Okay, so in its simplest form here, we've got our comparator with 2 inputs, A and B. and it's got its 3 outputs. Let's just put the number MSB to LSB 1101 with 0111. What do the outputs look like? Well, A is bigger than B, so it's got 100. But now what if A was part of another number? And what if B was part of another number? I've got to like an 8-bit number. Okay, I've got to find a way to pass information between two 4-bit comparators. Okay, if you can imagine this is the inside and that's the outside. Check this out. What we're going to add is something to the inside. Namely, A is greater than B, A is equal to B, A is less than B inputs from a previous stage. So, and then what's neat about this here is this right here could be the outputs for that stage be fed to another stage. So if you could imagine here, this is A3 to A0, and the guy below is B3 to B0. In reality, let's pretend that they're part of a 8-bit number combination. What are those? A7 to A4 and B7 to B4. What we're going to do is if that's the low order, what we'll do is have the high order comparator right next door. Now all I do is I route A7 to A4 to that one, B7 to B4 on that one, and this output goes to that one's input, this output goes to that one's input, and now what it's doing is it's saying, okay, in this particular circumstance, A is greater than B, A is not equal to B, A is not less than B, and then it's passing that information up to the high order. Now the higher order, let's say in the case of equality, let's say they're all quadruple zeros. Ordinarily, if there was no feeding input, it would say, oh, they're equal. Basically, it is now relying upon the logic for the lower order adder. I'm equal at this point. Go ahead and check my inputs, namely these here. Is anything below me greater than, equal than, or less than before it makes its final decision? And what it's seeing is it's seeing that A is greater than B. It's going to go ahead and signify that. Question remains is, what do I put here on the low order comparator? What are my inputs? Well, if it really is A3 to A0 and B3 to B0, implying that that is the lowest portion of it, that is the LSB, A0 and B0 are in fact the LSB, well, what's the previous relationship? Well, they're equal. What I need to do is put a 0 there, put a 0 there, put a 1 there. Okay, so your lower order comparator on its input, the A equals B input, will always be tied to 1. And what it's going to do is take its output being fed to the higher order or the next higher order. If you're going to do like a 12-bit number or a 16-bit number, its outputs are being fed to the next highest stage's inputs. And now it can make that comparison. So let's use this exact same relationship we came up with here. I'm just going to put some different numbers on here. Let's see if you can think how this thing works. Okay, so we've got A7 to A0 taking these values, and we've got B7 to B0 taking these values. So let's use the one on the left as our low order inputs. So what I'm going to do is I'm going to take A3 to A0, put them on our A inputs, B3 to B0, put them on our B inputs. What am I going to do on the low order equality and inequality inputs? Well, the one previous to the one lower than the LSB, well, it's 0, 0, 1. Got to do something with that low order inputs first. What does my low order outputs look like? Well, if this is being sent to my low order, that being sent to my low order, I've got a case of quality. And now what I'm going to do is take those outputs, feed it to the next stage's inputs, and now it's going to make the decision. It's basically the low order saying, hey, everything on my end, they're equal. I can't make a decision if this is an 8-bit number. It's up to you, the higher order adder. It's almost like we're in this situation right there. What are my inputs for that higher order adder? Well, it's 0, 1, 0. It's saying everything below me is equal. You get to make the decision. Go ahead and tie A7 through A4, 0001, 0010. Which one is bigger, 1 or 2? Well, to me, binary 2 is bigger. So B is bigger, and that is our final output. The number B7 through B0 is greater than A7 through A0. So it's this concept of cascading inputs. Let's talk about 1-bit comparators. We talked about having 3 inputs in there. You could also kind of streamline this. You can make 4 inputs for a 1-bit comparator. One would think that I'm going to have to do A and B, and I'm going to have to do an A is greater than B, A is equal to B, A is less than B inputs to come up with A is greater than B, A is equal to B, A is less than B output. So it's 5 ins, 3 outs. One would think that you'd have to do that for a single bit comparator. And then if I wanted to use a structural approach in VHDL, I would have to take this model and hook it up with another one next to it. And if I wanted to make a 3-bit comparator, hook up another one of those. You can kind of trick this thing. You don't necessarily need that A equals B input or output, because if that's 0 and that's 0, what is A equals B? Well, it's equal to B. Because you're using that property of 3 outputs, only one can be true. If that's false and that's false, obviously A equals B. That being said, your final comparator in the MSB position does have to have that, okay? Because you want that 3 final outputs. So what you might look if you tried this in a structural approach is something like this. So you want to make a 1-bit comparator. There you go. You've got 2 numbers, A0 and B0, and it's taking your 3 outputs. A is greater than B, A is equal to B, A is less than B on the left-hand side, and it's got 2 inputs. A is greater than B, A is less than B on the right-hand side, and all I'm going to do is say 0 on both of those. So what I'm doing here, what I've gained from this, I can do a 4-variable K-map expression to come up with a logical expression for this guy, the logical expression for this guy, and the logical expression for this guy. Okay, now here's where the magic comes in when you use the structural approach. You want to go make a 2-bit comparator? Just take that single 1-bit comparator and hook it up in the following fashion. Just don't hook up that output. It's unused in this particular case. All this comparator, all the next highest order comparator needs to know, namely this one here, all it needs to know is if it's greater than or less than. And again, what do you think you're going to do to make a 3-bit comparator? Obviously, just add another one. There you go. Go ahead and make a 4-bit comparator. And let's say that's where we want to go ahead and end. And now here is my final output for A is greater than B. Here is my final output for A is less than B. And then, again, looking from the outside world, here is my output for A equals B. What I'm going to do is basically put this thing in a larger box. And there you go. I've created a 4-bit comparator where I've got 3 outputs. A is greater than B, A is equal to B, A is less than B. And I've got my 4 inputs for 2 numbers. So let's say I've got 2 4-bit inputs, and then I've got 2 cascading inputs that I can use. Okay, if I wanted to create an 8-bit comparator, what I could use is the component instantiation of a 4-bit comparator. Okay, so this is another example of how that structural approach can you save some serious time and money. Is this the only way to implement a comparator? The answer is no. Okay, this is just the structural description. There are some pretty powerful behavioral descriptions that we can implement a little bit later on, which we'll show you guys in lab or later lectures. This kind of concludes for comparators here. Let's move on to our next common function of combinational logic.